Righto. This one shouldn't take too long. Just going to talk briefly about what controls metal deposition. So we've sort of looked at where the fluid comes from, what it can do to other rocks, and the final mechanism is how does it drop out metals. So just going to look at the controls or what leads to the deposition of metals, and as you probably started to become aware of, we've looked at them in various forms in terms of alteration and the nature of the fluids to begin with, and in many respects you can almost look at this process as the reverse of how metals are transported in the fluid to what changes so the metal then no longer is happy in the fluid and drops out. So the main thing is the temperature, pH, redox, controlled by mixing or reacting with host rocks. So metal behavior, we've touched on this a bit. So you can revise things like the Lewis and Lewis hard and soft acids. So looking more at what metals combined with in terms of we need that negatively charged anions, the ligands, for metals to complex within the fluid to be able to transport, and different metals have different anions that they like. Base metals quite like chlorine, things like gold prefer bisulfates and things like that. So those become important about how the metal will actually drop out. And so the concentration is not random. We have to have this focusing. We need that metal in the source, and we need it to be concentrated in one particular point. So for an ore deposit, you don't want that spread out over kilometers. You want to have it nice and concentrated. So ideally you want something that leads to a rapid change where you're interested in the metals. And I'll touch a bit more on this maybe later today or tomorrow. Different metals behave in similar fashions. That's based on that sort of control of the ligands. So many of them will be transported together and deposited together, or maybe potentially in a zonation around an ore deposit. So the chemistry of the metals, it's governed by the fluid chemistry, as we've touched on previously. So pH, redox, salinity, activity of certain ligands. And remember, those complexing of metals is important, and that will actually influence how things are deposited. And then we can look at compatibility of elements, which I'll go to in a second, and partition coefficients, and other controls on metal deposition. So ionic radii is very important because this influences how elements are likely to bind in structures, and their valency state is also influential to their transport and deposition controls. And so we have broad similarities of metals where they can lead to similar behavior. So compatibility is just a fancy way of saying if something likes to be in the solid material or in the fluid. It's largely based around magma, but similar process can apply to looking at it in terms of solids and fluids. So the element that likes to stay in the solid is called compatible. The element that likes to move into the liquid or the fluid is called incompatible. So that's the broad distinction. So something like, the classic example is something like water in a magma. Water likes to behave in an incompatible manner. It likes to go into the magma. And this can be quantified by what we call a partition coefficient. So that's just a ratio of how likely it is to move into the fluid versus staying in the solid. So you have different partition coefficients depending on the elements you're looking at. So some might have a very low number, some might have a very high number. So if it's close to 1, it likes to be in the fluid. If it's closer towards, or sorry, if it's greater than 1, it likes to be in the fluid. If it's less than 1, it's incompatible. So this can be extended to the fluid phase, like I discussed. We might just change the subscripts to an F, and the concentration of the element in the melt. So if we're looking from the egress of fluid out of a magma. So if it's greater than 1, it's more compatible in the fluid, it likes to be in the fluid, and it'll partition into that fluid. And if it's less than 1, it'll stay in the melt. So it's a way of just quantifying how things behave, and it's largely based off experimental work to decide how that number comes up and what it means in terms of the system of interest. But the key part is that generally metals like to be in the fluid, less likely to be in the melt or the solid residue. So one of the key variables for controlling metal deposition is temperature. We've covered temperature a few times, so it makes sense that if temperature influences how metals go into the fluid, they also influence how metals drop out of the fluid. So when we decrease the temperature, we may trigger instability in those metal complexes, so the binding of the metal with the ligand, and this results in the precipitation of the metal. So it gets to a point where it doesn't have a way to sit happily in the fluid anymore because it's not balanced by the negative anions, and it drops out and precipitates as an ore mineral or a native element potentially. So a simple example might be copper precipitates out as chalcopyrite, so as a copper sulfide. So the nature of that precipitation will be controlled by a few things, like the composition of the fluid, its pH, salinity, etc., and the nature of the host rock that it might have reacted with. And generally, metal solubilities decrease with temperature, which broadly makes sense. And the cutoff is generally around 100 degrees, 150. So here's a graph, which is a quite nice depiction of metal solubility with temperature. So high Y values mean metal is more soluble, so there's potentially more metal in the fluid at those conditions, and temperature on the x-axis. So we can see different behaviors, but we see a general decrease in the metal's behavior as we go down temperature. Specific metals have slightly different behaviors. In this case, the change for zinc sulfide is less than potentially moly, okay, and gold. And so, the temperature of these fluids is, when they deposit those metals, is likely to be hot, probably much higher than some of these other base metal systems. So that's why you can get subzonation associated with variability in the temperature of the fluid as it moves through. It might drop out certain things early, and then other things that are still soluble at those temperatures can be transported further away. Another one is increasing pH. So this time we have quite distinct behavior with things like the base metals. Solubility strongly decreases with increasing pH. So they're much happier in low pH fluids. And so if we can somehow change that pH of the fluid and increase it, we might lead to the deposition of those metals. Moly and gold have a sort of an inverse relationship. Gold is a little bit more complicated, but they have distinct behavior where they are quite soluble in high pH fluids, and that relates to their main ligand binding factor in the fluid, where they're probably more controlled by sulfides than chlorine. And this becomes even more apparent in salinity. So these ones are these base metals commonly bind with a chlorine complex. So if you decrease the salinity or component of sodium chloride, you actually lead to a deposition. Whereas gold is mainly associated with a bisulfide ligand, and so its behavior is less impacted by those changes. Redox, or sulfur and sulfur fugacity. So for everything we're looking at here, except for gold, the solubility of the metals decrease with increasing sulfur fugacity. Because gold complexes more favorably with a bisulfide, its behavior is distinct. So its behavior increases with increasing sulfur fugacity. So if you have more sulfur in the system, or change that sort of nature of its redox, gold will be happier. So if we can change that balance, gold will precipitate out. But for the base metals, the opposite is true. So, you know, we can look at various forms of details of this. This is sulfur fugacity, looking more specifically at the different sulfide minerals and when they're stable. But in essence, pyrrhotite is stable at lower sulfur fugacity versus pyrite. But it's not always true. They can coexist together, and we can have different details. But the other thing from this diagram, these red numbers relate to the iron content in sphalerite. So at higher temperatures and lower sulfur fugacity, you can actually incorporate more iron into the zinc lead sulfide. So this can also affect the potential grade of that ore mineral based on the conditions of that system. So how do we change the nature of the fluid to lead to metal precipitation? Cooling is an obvious one. So fluids, you know, are going to progressively cool. If they can cool rapidly in one point or below that threshold, you can deposit it. Boiling, you can depressurize the system. You could mix fluids. So you mix meteoric fluids with magmatic fluids. You'll get a change in that composition. You might go from something fairly non-saline to very saline, or oxidized to reduced, and that can change redox conditions or salinity of the system. So cooling is one of the most efficient, especially if reduced sulfur is present. This is common in volcanic and magmatic systems as the fluid moves close to the surface. Boiling also leads to a cooling of the hydrothermal fluid, but it also can lead to a separation of components, particularly the ligands, as you depressurize that system, so then the metal is left without a binding complex. So particularly causes sulfur to fractionate to the vapor phase, destabilizing the metals in complex. And this can lead to zonation, where you have different times where those ligands behave differently. The sulfide might depressurize early, and the chlorine may be stable and take the base metals further away. So you could get things like copper in a proximal zone because it's associated to the sulfides, whereas the base metals can move more distal from that system. Fluid mixing, fairly self-explanatory, but they could be related to different temperatures, different pH, different redox. Water-wall rock, so this is tying onto the alteration. So depending on the nature of that alteration reaction, you're changing the nature of the fluid. So we could neutralize the fluids by interacting with an acid buffering mineral. This is classic for carbonate. So that's why skarn's quite common, because you can, you're interacting with an alkaline rock. But also feldspars can do that because we can liberate hydrogen. Change in redox. So, you might have fairly reduced organic shales where biogenetic processes have made them fairly reduced, and you interact with an oxidized fluid, or you can scavenge sulfide complexes that can destabilize the gold in that system. So that's that part. I'll just pause this for a second. So this lecture is more looking at which metals behave together and some of their chemical behavior. So, a lot of this is, there's a lot of detail here that you don't have to memorize all of it. It's just more to go through it, sort of identify why things will behave together. So don't freak out by lots of specific details. But these are the sort of things we'll go through: the valency, common mineral species, behavior, and how they can concentrated or transported. So iron exists as ferrous or ferric. I think most people are fairly comfortable with that, so therefore it's strongly redox controlled about which iron is going to be stable. Is it the Fe2 plus or Fe3 plus? So ferrous iron, Fe2 plus, is generally more stable in fluids than the ferric iron. Okay, but of course, what's stable at the surface is a distinct story. Common ore minerals: hematite, gorthite, potentially limonite. But hematite is a classic one. It's the oxidized Fe2O3 variety, which is common in banded iron formations. In magmas and things like that, reduced environments, ferrous iron is more common, and we know that as magnetite. You might see it in pyrite, pyrrhotite, those sort of things, as well as being in the common rock-forming minerals. So this is just a diagram showing the controls of pH and oxidation state on the stable form of iron. So here's our fugacity of oxygen, which we can, fugacity is really just like an activity. And so in this case, when we look at oxygen fugacity, just think about it as a redox potential, so a redox state. So higher in negative numbers, higher oxygen fugacity means it's in a more oxidizing environment. Therefore, we will stabilize things like hematite. There's no magnetite on there, but yeah, at more reduced environments, we'll get things like pyrite and pyrrhotite. There's magnetite there. But depending on the pH, we can also influence things like magnetite stability, association with its different relationships with the aqueous species. So this is outside of a fluid. Okay, so it's just some specifics in the phase diagram. So here's another diagram. In this case, we're looking at the activity of oxygen, or fugacity, versus the activity of sulfur, or its fugacity, so proportions. So in this case, we have available oxygen, we can form hematite. If we have less, we can form magnetite. in terms of sulfur, if we have more sulfur, we might find pyrite, whereas if we have reduced sulfur, we'll form pyrrhotite. Okay, so that's what these sort of fugacity or activities mean. The common terminology should be activity, because we're looking at, we're not looking at gaseous states. We're looking at elements in the solid state generally. So it's the availability of those elements for the reaction. So that's just some specifics about where iron will deposit, depending on the controlling extensive variables. Here's a classic banded iron formation. Iron is very widely distributed, as we know. It's in many common rock-forming minerals. So we need a way to concentrate it sufficiently that it's not hard to extract out of things with magnesium and silicate. So banded iron formation presents a nice case where we can actually deposit it as hematite, and it's easier to refine. Okay, copper is a transition metal. It can exist in two common valencies as cuprous or cupric, so 1+ or 2+, but it also can form in its elemental state. Copper, its stability is complicated. In this case, we have a diagram looking at pH versus EH, which is another way of looking at oxidized potential. So oxidized versus reduced. So we can have it as 2+ in the oxidized environment, and then it gets more complicated down this way. In high pH, we can get native copper, and low pH, we can get it as cavellite, or in other solid phases and sulfides. But in this case, the main point to present here is if you go from native copper, you increase, you'll get cuprite, then you can get it as a solid oxide phase as we increase in its redox state. So these things become important about thinking, especially for copper, where it forms in terms of, is it in a supergene environment, so exposed to an oxidized fluid leaching, as the ore body is, the gossan or the ore body is exposed to air, you'll get things like cavellite, whereas if it's protected ore deeper in the system, you might be in chalcopyrite. So this is a bit more specifics about it here. So like I'm saying, so a common occurrence for copper deposits in like copper porphyries is you have, as the body is exposed to the surface, you have that oxidizing and leaching of those sulfides. So you might get things like chalcocite, cavellite forming blankets on the ore deposit. If you go further, you get things like malachite. Whereas, you know, further into the ore body, you're more likely to get things like chalcopyrite as the main ore phase. So, oh yeah, that's where they are. They're further down here. So, at more reduced conditions, you get chalcopyrite. So, many copper ore minerals, lucky you. Don't stress about remembering all of them, but you can see that what's stable is highly dependent on the controls of things around oxidation and where in the environment it's likely to form. So primary copper might be in chalcopyrite, sulfide minerals like bornite, and they're formed in reducing environments, whereas we can get secondary copper mobilized in things like supergene oxidizing environments to form things like chalcocite, cavellite systems. So yeah, here's some of the, can also be in secondary copper and carbonates, phosphates, etc. So that's why you can get a variety of different, here's malachite and azurite, so they're copper carbonates. They're quite common in that supergene or surface secondary environments. So they're just some broad examples. So it's mostly transported in saline chlorine-rich systems. Chlorine is its main ligand preference. Again, concentrates in a variety of environments because of this behavior. Common ones are igneous, late stage igneous. You can also get it in sedimentary environments, metamorphic systems. One of the common cases is supergene environments related to things like porphyry deposits, like in the Andes. So they'll actually mine the copper blankets and then get into the other deposit depending on the grades, and that controls its ore value. Lead, so two forms, plumbus and plumbic, 2+ versus 4+. It is not that affected by redox. Plumbus is incompatible in most common crystal structures, so its valency straight limits its ability to substitute in. And we'll go through some more of those briefly. Here's lead. So galena is mostly formed in reducing environments. That's the common ore mineral. When you're oxidized, you might find anglesite, crucite, depending on the pH. Lead is relatively immobile in the environment as it informs insoluble precipitates and strongly onto hydrous oxides. So, which is thankful that it's not, highly mobile and moving around, because it's carcinogenic. So, it stabilizes with a variety of these acids. It's a borderline acid and stabilizes with these main ligands. So it likes chlorine, it's base metal, but it can also bind with bisulfites and things like that. Quite common out of sedimentary environments, because base metals are common mostly in sedimentary sequences, but you can get it in late stage igneous as well. Zinc, it behaves in a manner similar to lead. They are quite commonly bound together. Its main ore mineral is sphalerite, zinc sulfide. And so there's similar ionic radii, similar charge, enables quite tight pairing, so base metal deposits commonly lead, zinc, and silver. There's some more details specific to it. It's liberated in the environment more because you can oxidize sphalerite and it becomes soluble. And then it forms stable secondary minerals, carbonates and silicates out of that system. So things like smithsonite, zinc carbonate. You might get it in zinc clays, but other varieties of silicates. But the primary ore mineral is sphalerite. Silver mainly forms as 1+. It's a soft acid on the Lewis scheme, so it likes soft bases. Binds with bisulfates and chloride ligands, so it has a range of transport mechanisms. It usually, silver, sometimes we might find it as native silver, but it commonly deposits into other ore minerals. So commonly it's in tetrahedrite, but it can also, the most common ore deposit is usually in galena. It binds into that structure with lead sulfide. So lead and silver, very common metal association. But it also can be lead and gold, is also another common occurrence because it can move in those bisulfide complexes that gold likes. So, either if it's in a base metal, it'll be with chlorine ligands. In a gold system, it's commonly with a bisulfide. Gold, precious metal, generally forms as its native element. It doesn't have a valency state. Mostly bisulfide ligands, but it can travel with chloride complexes, though it's not as efficient. So that's why it has that distinct metal deposition behavior. And generally, it doesn't like to, similar to silver, you either find it as native, most commonly as native mineral, but sometimes you'll find it in things like pyrite, arsenopyrite, as what we call refractory gold. And so the metallurgy of those systems is a little bit more complicated than native. Can also be concentrated in the weathering environment. So you might dissolve pyrite and arsenopyrite by supergene processes, and then it can be transported as a placer. So it's heavy, it'll move around, but it's soft, so it stays in the surface environment for a long time, and that's why alluvial gold has long been a nice source of that ore deposit, because alluvium is much easier to mine than a hard rock. It's much cheaper to just dig up soil and process it. Again, it's found in diverse environments, commonly metamorphic orogenic systems, but you can also get porphyry or skarn and even subvolcanic epithermal deposits. So it's quite a wide range. Okay, nickel mostly exists as 2+. It is compatible in some silicate minerals, things like olivine, ultramafic. Behaves similar to iron and cobalt. And it mostly concentrates in two environments, a magmatic volcanic environment as a sulfide mineral called pentlandite, which may break down to other secondary phases, or in laterites, so where you form hydrosilicates from serpentine minerals. So laterites are a surface weathering effect, which can be a nice way. So you usually weather things like peridotite, which have high nickel concentrations, and you actually concentrate the nickel in that weathering environment. So one of the big nickel deposits is in New Caledonia, where you have one of the biggest ophiolites or peridotites exposed in the world. So yeah, that's sort of covering that. It's concentrated mostly in these ultramafic systems, and therefore you need those cases at the Earth's surface to form those laterites. Otherwise, you can form it in ultramafic basalts. Ultramafic basalts, ultramafic lavas, and you can get where it will be immiscible and drops out of the liquid with other sulfides, and that's like the Alba province in WA. And we'll talk a bit more about the specifics of these ore deposits later. Lithium occurs as 1+, is an alkali metal and behaves similar to sodium. So it will move into felsic systems preferentially, because sodium likes to be in the felsic environments. So pegmatites are a common lithium source, and lithium mainly substitutes into common rock-forming minerals. So one of the common ores is spodumene, a lithium pyroxene, or lepidolite, which is a lithium mica. But at the moment, the most economically favourable lithium deposit is as a brine in salt environments. So you weather it out of volcanic glass, and then it sits as a brine in salt lakes and evaporates, and it's much easier to extract. So pegmatites, yeah, we've gone through that. Tin occurs as 2+ or 4+, borderline acid, complexes with range of ligands, but commonly chlorine. Most important one is cassiterite, so tin oxide, and it's hard and refractory, so alluvial tin has been the main economic deposit for a long time. But it can also form in a sulfide mineral called stannite, but it's less common. Most tin ore is cassiterite. So it's mainly a magmatic process, like pegmatites and granites, and if we have a fractionation and it forms in these late-stage magmatic deposits, and if you can erode them, tin will survive in the environment for a long time. Uranium, more complicated because it has a variety of valency states, and so secondary uranium can be quite an important deposit. One of the main ore minerals is a mineral called uranite, pitch blende, and yeah, I won't linger too much on them. But yeah, there's a variety of uranium minerals, and it's concentrated in a variety of environments. So it can be things like strongly oxidized I-type granites in the late magmatic fluids, like Olympic Dam, but it can also form in evaporation and arid environments as a calcrete, as a secondary surface product, like in Western Australia. So slightly more complicated. Manganese, 2+, 4+, strongly governed by oxidation, borderline base, complexes with hydroxyl or chlorine. 2+ is more soluble than 4+, and so it's carried in solution in reducing environments. So it's ultimately derived from seawater, so it's quite common in seafloor sediments. So if you can metamorphose them, or in things like Broken Hill, you can get precious rhodonite or rhodochrosite, so manganese carbonate or manganese silicate is one of the main deposits. But we can also get ore minerals as pyrolusite, manganese oxide. So manganese is quite easily weathered out of rocks. You'll commonly see a weathering rind or many rocks with that dark black color, which can be a form of pyrolusite. Okay, tungsten exists as 6+. It's a hard acid. Most important ore minerals are scheelite, calcium tungsten oxide, or wolframite, iron manganese tungsten oxide. So concentrated in reduced environments, mainly in magmatic fluids, but commonly in skarns as well. And tungsten is an important pathfinder for gold deposits. Arsenic, yeah, there's a range of details here about arsenic. I don't necessarily need to go through them. Antimony behaves similar to gold and has a complex structure. Its main ore mineral is stibnite, and the main ore mineral for arsenic is arsenopyrite, so in these sulfide structures. Molybdenite occurs as 6+. Molybdenum occurs as 6+. The main ore mineral is molybdenite. Very soft, malleable, hard acid is molybdenite. Moly behaves as a hard acid, commonly associated with gold, copper, but also some tin and tungsten, and mostly transported in magmatic fluids. Platinum group elements, a range of them: platinum, palladium, iridium, osmium. These are mostly concentrated in layered magmatic intrusions and can be associated with things like nickel. So they're mostly associated with ultramafic rocks. Rare earth elements, flavor of the month, They're not so rare, as you're aware. These are the rare earths down here, the lanthanide series. But you know, people will pull up in a variety of other elements there, so just take care. Things like yttrium, magnesium, rare earths, but we have other rare metals that people are clumping in with the so-called rare earths. Their concentration in all minerals is more complicated, but it depends on which ones you're interested in. You can have things like zircon, which can have high concentrations of particular rare earths, brannerite, xenotime, monazite, for things like the light rare earths, cesium and things like that. You can also have apatite, so a phosphate mineral. You can also have allanite, so an epidote style mineral that take on certain rare earths. And they're particularly interested in things like monazite, xenotime, potentially apatite, because they're easier to process than things like zircon, which is highly refractory, and then silicate. Variety of different deposits. At the moment, people are chasing things like carbonatites, so weird carbonate magmas, placer deposits, and things like basalts where we can concentrate zirconium. So that's all the stuff. Good for us, we did it in one. Like I say, lots of detail, very dry. The broad thing is to start to put together metal associations and why that is, largely around things like ionic radii, valency state, and how they behave in hydrothermal fluids. So what ligands they're complexing with is a big control. And we'll start to get into those main ore minerals and why secondary ore minerals can be important as a deposit style, and how that's controlled by things like oxidation or pH, things like that, and environment, of course. So, excellent. There we go.